Hey everybody, welcome to Earth and Time, a channel where we explore Earth history as well as human history. And today I'm really excited because we're going to explore one of the major geologic features in the United States that has probably the largest effect on history for us, and that is the San Andreas Fault Zone. So I'm going to take you on the San Andreas Fault Trail just outside of Palo Alto, California, south of San Francisco, about 30 minutes or so. And we're going to do this hike and look at some of the rupture zones from the 1906 earthquake that flattened San Francisco. So come join me today. Let's check out the San Francisco Fault Trail. Let's get to it. I've made it up to the San Andreas Fault Zone, and check out that view behind me. So that valley behind us is actually the fault zone, and you can see the clouds and the mist back there in that spot. I'm really excited to do this hike, share some of the observations about this fault zone and about the 1906 rupture, which apparently we can see some evidence for on this trail. I will say, anybody who ever comes and wants to do this trail, it's absolutely stunning. Look at the clouds rolling in, the sun rising in the background, and the main fault strand comes right down that valley. It comes right in front of us behind this hill, and we're actually going to hike along it on the other side of this fence. So this is called the Los Trancos Open Space Preserve. I went ahead and grabbed a map, so we'll follow this along, and I'm going to look for some markers. One thing I'll point out right now as we start is you'll see these white markers. This is marking one of the faults here that are part of the San Andreas fault system. So they've actually marked the line for the fault zone. And you can see they actually have white marks on them. So this shows minor fault traces. And then the main fault trace will be marked with yellow. So it's worth mentioning that most of us think of a fault, or people call them fault lines, as a single strand. However, fault zones are made up of multiple faults. In fact, we call them fault zones as geoscientists because it's not just a single strand. I've got some friends hanging out with me over here, some deer that are there. Hi, deer. That are checking out the fault zone as well. And there's a guide marker. We're going to go to the Nanette Honco San Andreas Fault Trail. Although I'm here to check out the geology, I gotta say these trees and this trail and little tree tunnels here are pretty spectacular. As I'm working down some switchbacks down into the valley, this valley that's in front of us, I'm pretty sure is the main strand of the San Andreas Fault. It exists as a valley because the fault's running right down the middle. So there's one hill across the way. And then of course, I'm on the other side of the hill here, and running between us is the fault zone. Look at the trunk of this tree and all this moss. Wow. Oh, I just saw turkeys up here also, but I wasn't able to catch them in time to show you all. I had no idea there were wild turkeys here, or I don't know if they're people's pet turkeys that are running around here, but they're turkeys. I'm working my way down and down like Alice in the rabbit hole here, but instead I'm going to end up in the land of the San Andreas Fault Zone. Well, I found station 3 for this trail, and this is just really talking about this idea of the benches. Now, what's really cool about this is if you look over here, you're going to see the yellow markers, and the yellow markers actually mark where the San Andreas proper is going through. So here's something cool to do. The post is back here. So right now I'm actually standing on the Pacific plate. I'm on the North American plate. I'm on the Pacific plate. I'm on the North American plate. And now the boundary is going right between me, and I'm on the Pacific plate and the North American plate right here. How cool is that? Actually spanning across two of these great plates right along the San Andreas Fault Zone that you can see marked by these posts going behind me. In fact, if I look down here, the fault trace goes right past this fence, right down in this area, and you'll see there's kind of a steep side. There's a little gully and another steep side. So where these faults go through end up being zones of weakness. So water a lot of times will travel down these features. They'll accentuate the fault zones, and erosion will preferentially follow where those paths are of weakness in the Earth's crust, like the San Andreas Fault Zone. So you get a lot of different features that form on these fault zones. There's things called sag ponds, which are long linear ponds that follow that trend instead of a pond or a lake being more rounded, they're more long and narrow, and we call those sag ponds. You'll also get what we call these pressure ridges, and that's where portions have been popped up relative to other parts of the fault due to the pressure of movement and little bends and little deformities along the fault. Maybe we'll see some of those. In fact, where I actually walked down was probably one of these little pressure ridges along the fault zone coming through here, which is what these trees are on top of. So we're coming up to a kind of a cool spot that's showing an offset fence. Now, there's lots of pictures showing different kinds of offset of the San Andreas Fault. The San Andreas Fault's what we call a right lateral fault. So let me go to my trusty whiteboard and share that with you now. So here's my trusted whiteboard Walter, or Walt as I like to call him. And what I've done here is I've drawn two pictures of what are types of strike slip faults. And so this is a bird's eye view. So picture we're looking down onto the earth. And the San Andreas is this kind of fault. So this line represents the fault line. And you'll see I have two arrows with dashes on it. So these dashes at one point would have been together, but now they've moved relative to one another. So imagine if there's a fence across here, and we're going to see an example of that actually on this hike where a fence has been offset right laterally just like this. So we can see relative from one side of the fault to the other, it's moved to the right. So if I'm on this side of the fault looking this direction, it's moved to the right. Conversely, you can have left lateral faults where everything moves to the left of the opposite side you're on. So if I'm standing here looking across, I could see the fence move to the left. So those are the two types of strike slip faults that we talk about. And we're going to look at today the San Andreas Fault Zone, which is a right lateral strike slip fault. I'm looking down the fence line now, and we can see where this fence line is. And if we go over and step to our right, is the next fence line. So what we drew before is the fault would be running right between those two fences. And because the fence line across from us moved to the right, we would call this a right lateral strike slip fault zone. And so you can actually see that offset here along this fence. So it really accentuates that idea of that these fences were all once would have been lined up and now have stepped over. Now, this is an example. They've rebuilt this here so that way individuals can see how much movement's actually taken place along the San Andreas Fault, specifically during that 1906 earthquake. And here I am for scale, and you'll see, I don't know, let's see how far of a walk this is. It's kind of 1 foot, 2 foot, 3, 4, about 4 foot gap here. I know north of us, they had much larger gaps. So during the 1906 earthquake, the energy was starting to dissipate this direction and you didn't have as much offset. Now, where they're showing this offset actually is along one of the more minor faults of the San Andreas Fault. The main San Andreas Fault strand is actually down below us, and that would have had probably a similar amount, maybe a little bit more offset there in the 1906 earthquake. But again, this is just an example of what if the fault moved right here, how much offset you would see on a fence that was once all together that has now been right laterally separated by that strike slip fault zone. You can see where they actually marked one of the minor faults as part of the San Andreas coming right down where this fence is offset. And I'm guessing the main fault zone's down there in the valley. That's why we have a valley down below us. Although it's hard to tell today because we've had rain, there's actually a bunch of water popping up along the fault zone here, creating all this shrubbery that we see here right along the trail. In fact, you can see some of the water here. Although again, we've had rain, there's actually a spring that comes up here. So faults are great places to find water because they're zones of weakness and allow water to come to the surface. So plants love tapping into fault zones because they can get an abundant amount of water in those areas. And this hill that's next to us that gets really steep really fast is along the same strand where we see the offset fence here. And there's a lot of really happy plants running along this where they're tapping into that fault zone to get water easily. All right, we've come to the fork in the road. We're going to our left. I'm going to hike this direction. So here's another marker for the San Andreas Fault. One thing I'll point out is the topography associated with strike slip fault zones is very complex. So we saw where the strike slip fault zones create valleys, they can create ridges, but they can also create these flat zones where they've been filled in and have become stabilized crust or surface because maybe something pulled apart, you had some landslides come in or something else happen, but it actually creates a flat bench as well. It's fascinating to me how these strike slip faults work and their topography. I definitely think they're some of the hardest types of faults to understand. Normal faults are pretty straightforward. There's complications, Thrust faults are pretty straightforward with some minor complications, but strike slip faults, you get both normal faults and thrust faults as part of them. You get valleys, you get ridges, you get benches, flat spots. It's just all over the place because of the dynamic movement and the types of rocks they're going through and what's happening with the geography and the weather all changes how you look at these features. Coming up again to the main strand of the San Andreas. So here we go. So right now I'm over on the North American plate. And we see over here, in fact, actually you see there's a tree that fell over. I wonder why the tree fell over, but there's actually the run of the San Andreas goes right through here at this point. Work my way over. This is what we call a sag pond. Even though it's been raining, it's hard to tell, but if we see where the San Andreas Fault runs right through here, there's actually a little low. So there's a bench on the left-hand side, and then there's this little low that forms where water, if there's enough rain, will pool together and create a little pond, but it's linear. It's not as round as we usually think about ponds. It's a long linear pond, and actually you see some beautiful examples of these in Google Earth along the San Andreas Fault in this area, and I'll show those now. And as we can see, as we zoom in along the San Andreas Fault, just north of where we're at right now, we can actually see one of these sag ponds that really is a sag lake along the San Andreas Fault zone. You can see how it's long and linear as opposed to more what we call equant or more circular. And this is a classic definition of what is a sag pond. This would be a nice example of a sag pond, or an area that's opened up during the faulting of 1906 and created this long linear catchment for water. I mentioned earlier about how flora and plants will find these fault zones as zones of weakness and get water. So vegetation tells us a lot about what's happening in geology. And this is a really fantastic spot to look at as well. There's some really unique tree features here that I want to share with you. And if you can see underneath this brush, there's actually a 90-degree angle to this tree. They cored this tree and they found out that it was alive during the 1906 earthquake. And what they think happened is this is the main trunk of the original tree. The tree fell over in the 1906 earthquake. And then the tree branches popping up, they've dated to about 1908. They're doing tree ring analysis. So that suggests that this tree was actually involved in the 1906 earthquake, fell over, but still had enough root strength and was able to start growing upwards, reaching towards the sun again so it could survive. Really cool story, and a snapshot of damage that's still here from the 1906 earthquake. And I will say, quoting Jurassic Park, life finds a way. Here's another nice example of one of those trees that fell over and was working its way up after the 1906 earthquake. This also tells us that that 1906 earthquake did indeed come right through this region here. Now we're working our way on the trail down into the adjacent valley, and I am seeing some fault markers down here, but it looks like there's some of the offshoot faults or minor faults to the main San Andreas strand. Sure enough, here are some of those white markers showing a minor strand coming off of the San Andreas Fault, cutting right through and down this path. Is pay attention to the topography. So you have a little hill here, a little low, a little hill. What's interesting about some of these little lows is most of the time when we think about a low along a hillside, it's cutting perpendicular. So it'd be cutting down across it as streams start eroding down into it or water erodes down into it. What's interesting about these is actually they're working parallel to the contour line. So these are these kind of almost sag pond concepts or drainage concepts associated with how the strike slip fault sets up the topography here, which is very different than how we think of water running down a normal mountainside or hillside. As a geologist, we look for these clues, not just the vegetation, not just the topography, but how we think water would run down as well into these areas. And that can give us an idea about maybe what we're seeing for the types of faulting and how we think the fault is moving. We're back at the San Andreas Fault marker, and actually here's another bench. So what happens with this bench is as this stuff's sliding apart, right? And I didn't explain this as well probably up above, But as they slide apart, then it fills in. Then they slide apart and it fills in. There's little gaps. So you slowly can build a bench here if water's not coming through that region. And that's one of the reasons you'll see these flat spots running through this section of the San Andreas. And so here's another post, but that's why you can see it's flat here, because it opens, the cracks open, they fill, they open, they fill. And if there's not water that goes through this, which, as we know, the topography here plays an interesting role, and the fault plays an interesting role, and subsequent small faults all play interesting roles on how water travels. So if the water's missing this area, you can actually create these flat benches from where the faults move through time. Along the San Andreas Fault, so the next question everybody always thinks about is, well, when's the next big one going to occur? We know we had the Loma Prieta one back in 1989, a major earthquake here, major fault movement at that time, and that's southeast of us from where I'm at right now, along this portion of the San Andreas Fault Zone. In fact, I'm walking past a marker right now back here. But we don't know, right? So what we can do is we can work on being prepared. And there's lots of websites out there. There's lots of material on how to be prepared for an earthquake. And it's similar to those of us who live in Houston, where we have to have 5 to 7 days of food prepared in case there's a hurricane, and we have extra batteries because a lot of times we lose power. We know how to shut off our gas. We know how to shut off our water. Those are all important things to know if you're living in this area as well, because emergency preparedness is the same for most natural disasters. Check out those websites. I'll put some down in the descriptions below that you can check out about how to be prepared for earthquakes and what you need. We don't know when the next big one's going to hit, but what we can do is be prepared for it. Main fault zone runs, I think, down that hill from up there, across this topography, down to where I was at to the right. Here I'm coming up to a little drainage divide where water is running down here. It's not running right now, but we can see where water runs through, comes out the other side, and runs down the valley. If you're ever in the Silicon Valley area or working up Highway 1 along the Pacific Coast, it's about 30-minute drive up to this spot from either side, roughly, and well worth doing. This nature preserve area is absolutely spectacular. And you get to learn about some really cool geology that really does affect everybody here in Northern California, and really across almost all of California, where most of the population centers are all affected by the San Andreas Fault or the subsequent faults related to the San Andreas. And look at that, there's a bench on a fault bench. With this amazing view behind me set up by the San Andreas, I want to thank you all for joining me today and learning a little bit more about the geomorphology and the geology of fault zones, specifically strikes of fault zones. If you haven't already, please give this video a thumbs up if you enjoyed it, if you learned something new. Make sure to subscribe if you haven't already, so you can keep up on all my adventures, learning about geology and history and where those two things intersect with our lives, human lives. So with that being said, thanks again. We'll catch you on the next adventure. Take care.